So we are going to open our cadence schematic that has the example here, and I'm going to explain you exactly what it is in this schematic, because the template that we have here we are going to use for any kind of negative feedback circuit. So our circuit is here. We have this block that we already created in lab number 2. That is our small signal model. We can just go internally to see again how it is. So it has our transconductor, gate to drain capacitance, gate to source capacitance, gate to bulk capacitance, RDS, drain to source capacitance, and drain to bulk capacitance. So all the small signal model. And I have put the feedback resistor RF, load resistor RL, series resistance RS, source resistance, and we have a voltage source. This voltage source I put V in, so I will be able to control the value of this one in the simulation environment. And here also you can see for the small signal parameters I have them also as variables, so I can control them from the simulation setup. Something that it is interesting is that I added this current source. This current source I am using a variable IT to control it, so I can put it 1 or 0, I can switch it on or switch it off, and you will see that it's very handy because then I can play with the switching on or off voltage source, this current, in order to extract the loop gain or other parameters. So there are many ways to do this. This is the one that I recommend you. You can use the ADXL. And I have created 4 tests here. I have created a test for the closed loop gain, AF, the asymptotic gain, loop gain, and root locus. So let's go very quickly explaining each of these ones. So I double click here, I get the test for the test bench for the closed loop gain. In the closed loop gain I am only interested on AC frequency, so I want to have a body plot of the amplitude. And then I will be also interested on checking the pulse 0 of the closed loop gain. So I have this, and then I just plot the V out and pulse and zeros. So I can actually just let's disable these ones. Let's run a simulation. Okay, it is done. And then this is the information that I have for this test. Let's have a quick check. Put a marker here. The closed loop gain that the simulator tells me at low frequencies is 9.55. Okay, it is 9.55. So let's go back to our calculations. It is 9.55. It is exactly the same. So we did the correct calculation using the asymptotic gain model. And then I have the final position of the poles that give me the bandwidth of the circuit. We're going to talk about that a little bit later. Again, to find the position of the poles, I run the pole 0 simulation. I have to select the output node for the calculation of the pole zeros, and then the input voltage source. I can select if I want to take an input voltage or a current source, and then I just select using the this option here. Okay. To plot the pole and zeros, when the simulation is done, you have to go to results, and then you go to direct plot, main form, you put pole 0, and then you click add to outputs and plot, and that will add the pole and 0 to the list of simulation results that is going to save and plot. Okay, so it will appear here at the output setup. Okay, and of course you have to save the output signal also, but that is easily done with output to be plotted. Select on the sign, and then you select the node, click, and then it will be saved. Okay, that is the template for the closed loop gain. Now let's take a look to the asymptotic gain. So I will to do like this. So for the asymptotic gain, what I'm going to do, it is I'm going to set the transconductance to 1000. So it is a huge value for the transconductance. So I'm going to select the asymptotic gain here. You can do that here in design variables and set it manually here to 1000, or you can do it directly here. Now the other parameters that I have here, Vin is equal to 1 and the test current is equal to 0. Important, this is 0 and this is 1. They cannot be both at the same time, never. So I'm setting this to 1000, and then I can run the asymptotic gain. And I also save the gain and the zeros. Here in the output setup, I can give names to everything here. So I give it the name asymptotic gain to this one. I plot it, and then we see the asymptotic gain. Give me a value of 10, 9.9999. It is 10, which is exactly what I expected. At low frequencies, the gain should be equal to 10. It will be 1 mega ohm divided by 100 kilo ohm. So this is exactly what I expected. So let's take a quick look. This is what I calculated, minus 10. And more interesting, the position of the pole that I have here is minus 5.9 megahertz. This is position of the pole. It is going to be a 0 in the loop gain. So keep this in mind. We're going to check later if this pole in the asymptotic gain becomes a 0 later. Okay, so this is the asymptotic gain. Now let's make it a little bit more interesting. We go to the loop gain, calculation, and that is a little bit tricky. How to do that? For the loop gain, we're going to do exactly what we did on the board. We are going to disable this voltage source, and for that we're going to set this voltage to 0 volt, then it becomes disabled, and then I'm going to enable this current source. I'm going to put IT equal to 1. When I do that, then I can simulate the voltages at the gate and at the source, and extract the gate to source voltage, that it is my factor beta. So if we take a look to the setup here, we see that IT is equal to 1, and we see that the input voltage is equal to 0. Now I need to extract also the pole 0 of the loop gain. So for that I need to change the settings for the pole 0 analysis. The positive output node will be the gate voltage, the negative output node will be the source voltage, and the input will be my test current source. Okay, so this setting will guarantee that I extract the right pole and zero for the loop gain. Okay, so when I send this to simulation, let's send it to simulation. Okay, I am saving the gate voltage and the source voltage here. Why do I save it? Because then I will need to calculate my loop gain. So, how to calculate the loop gain? Well, we go to we need the calculator and the results browser. Let's go to the results here, and then we open also the calculator here, and then we check that we have the set for the loop gain here selected. That will take all the data from this test, and then first I extract the value of the voltage at the gate. So let's see, frequency voltage, we extract the gate, we test it, then it is correct, enter. We extract the voltage at the source, so this is the source, we test it, then it take it, that's correct. Then we subtract it, so we have a gate voltage minus source voltage, then we have VGS already here, we save it here. And now I need the transconductance. I need the transconductance value, and then I have a few options to do this. I can just add the transconductance as a value here, multiply this by the transconductance in this equation and plot it to get the whole loop gain. Or you can also do like this. Here I created another variable, and you can do this with global variables add variable. I just created a variable that is called GM, that I will keep it constant. That will be a copy of the transconductance that I have it here. So the thing is that I cannot use this one directly, because for the loop gain, as you can see here, I am setting this transconductance to 0. So I cannot use this GM1 as a parameter in the calculator, because it's going to be 0. But if I create a copy, I will be able to use the copy that is called GM. You can do this also manually if you want, but I just created a variable copy that it is GM here. So if we come back to the calculator here, you can extract that value from the result, the browser. And where is the browser? Let's open the browser like this. It is there. You go to the variables, and then here in the variables you have GM, that is the copy that I created. You click in value, and then you send it to the calculator. Right click and send it to the calculator. Then you have this one here. You can test it. You will see is 227 micro Siemens. That is correct. And then I just multiply the gate to source voltage. So I multiply it, and then let's test it. This will be the loop gain, gate to source voltage multiplied by the transconductance. So then we will have the loop gain, and then I can bring this equation to to the simulation setup. We go to the output setup, and then here in the loop gain simulation I can add an expression and bring it from the calculator here. Okay, that will be, and give it a name. For instance, AB new. And that is how you can put the you can save and calculate the loop gain and plot it. So let's run it to see if it works. Okay, AB new is 21. So I'm going to delete it because I already had it in my setup. So let's see, output setup, then delete output. Okay, let's send it to run. So it's 21.7. It is a low frequency loop gain, and this is exactly what it is calculated with our formula. We managed to calculate the loop gain very accurately. Okay, and finally in this template we have the root locus. So for the root locus I basically set again back the input to 1, the current will be 0, and then I will be swapping the transconductance, that is my amplifying variable, and that will be in the pole 0 simulation. So I set it back the pole 0 simulation to take the output from the output of the amplifier. The input will be the input voltage source, and then I swap the design variable transconductance GM1, and I have to do this manually. Unfortunately I cannot put the GM variable here, at least not in this version of Cadence. So it will start in 0 and then ending up in 0.227 millis, and then I give the number of steps and run it. So let's oh, okay, I need to enable the test. So I enable the test, send it to simulation. And then I have the root locus here for the poles. So let's take a look. 0. Transconductance 0 is the original position of the poles. And then I start increasing the transconductance. We see how the poles start moving because we are introducing loop gain there. So we introduce loop gain, and then they start splitting and then moving around the zero, the phantom zero. That phantom zero was around 6 megahertz if I remember correctly. We are going to check out very soon. And then they crash again, and then they become real and they start to separate. And they continue their trajectories, so we can until they go to their final resting points. Where are the resting points? That will be the points that were simulated in the closed loop simulation. Yeah, so very nice. We can basically reproduce the same information that MATLAB give us. We can check what is the trajectories of the poles when we introduce feedback in the system. Okay, so this is the setup, and we have checked that this is correct, this is correct. Now let's take a look the position of the poles. So we have calculated the position of the first pole at 5.77 and the second pole at 1.17. Let's take a look here. We can run only the loop gain simulation. So in the loop simulation we have one pole that it is 5.78 megahertz, and yeah, this is exactly what we calculated. We calculated 5.79, so it's pretty much correct. This works very nice. And the other pole, it is located according to the simulator in 660 kilohertz, and we are a bit off with that one because we calculated 1.17. and again we remember that the open circuit time constant, it is very simple. It will introduce some errors, and when it introduce some errors we will have to correct for those. So one of the things that we can do now is that start introducing CGD, and we start from the simple one. At the output node, CGD will be added to CDS, and then when we add it, the pole will be around 960 kilohertz, 670. It is not so far away. We can probably improve the model, yeah, but typically it really doesn't matter if we are a little bit off with the position of the poles. The method, it is not going to be perfect, the open circuit method, so it is just going to give us a first-hand approximation of the position of the poles. So we are happy with this. It is relatively close to what the simulator tells us. Then we can calculate the achievable bandwidth. For that we use the loop gain product, poles product, and we have two poles, so there is square root of this, and that will give me 11.23 megahertz. That is under the assumption that we have phantom zero that put the poles in butterworth positions. Let's also calculate if it is actually possible to have that phantom zero, and then we calculate that the sum of the two poles is 6.3 megahertz. That has to be smaller than the square root of the maximum achievable bandwidth. And then we can see that yeah, that is correct. So it might be possible to put a phantom zero. So summary of the simulations here. We have the asymptotic gain that gives a factor of 10. That's exactly what we simulated. We have a pole at minus 5.96 megahertz, and yeah, that pole in the asymptotic gain comes from the fact that we draw it again, plus minus minus plus. We have RS, we have RL, and then we have the voltage source here, VS with RS here, and then we had that when this circuit here behaves like a transconductance amplifier, it is converting this voltage into current, and then sending this current through the output. It has very high impedance, and when we put the transistor here in the middle, we will have the CGS appears between the gate. CGD will appear between the gate and the output here, the input and the output. And if this resistance it is relatively small, then there will be one pole that dominates here, regardless of this is a nuller or not. There is going to be this pole located at 1 over S. It will be CGD RL. So we will have this pole filtering the signal at high frequencies, and this pole that we have here, this will appear as a phantom zero. We will take a look now. So this is the asymptotic gain. The closed loop gain is exactly as we predicted, also with our asymptotic gain model. The equations here, we are getting that the bandwidth that we got for this circuit is around 6 megahertz. So the 3 dB bandwidth of this circuit, and the first pole is located at around 6 megahertz. And the loop gain also, we got that we calculated very accurately, 21.7. The position of the poles also, we get a really good calculation for the first pole, and a rather reasonable calculation for the our output pole. Now, something that is interesting is that the position of the zero here. The position of the zero in the loop gain, when we extract the pole zero, it was located at around -6 megahertz, and that is exactly the same place that we had the pole in the asymptotic gain. So this is a pole in the asymptotic gain, became a zero in the loop gain. Finally, we had the root locus, so we can see the trajectories of the poles when we apply feedback. The same information that we got in MATLAB, which can be very useful, in particular if we need to check what it is causing instability. So we are going to be plotting root locus very often. Okay, the next example will be a shunt stage amplifier.